So we are in chapter 5. Chapter 5, we're going to take on the topic of discrete random variables. In section 5.1, we're going to take a look at what discrete random variables are, and also we'll discuss probability distributions of these random variables. Now, earlier chapter, we did mention about discrete and continuous variables. And we defined them explicitly again earlier. So this is kind of a continuation of the work that we've already done. The only difference is the word random here. So what we've done is added randomness to our variables. And we're just going to talk about discrete here, not continuous variables. So let's define what do we mean by first of all, a random variable. A random variable is a variable whose outcomes depend on chance. Okay, so we don't know the value of those variables ahead of time. So for example, how many children live in a household? We don't know that, so that's a random variable. What is the rent, a monthly rent an individual pays that in a given location? We don't know that either. So the values that we haven't observed yet become random. Now, if these values are countable or finite, then they become discrete. So a discrete random variable is therefore a random variable whose values are finite or countable. Okay, so here I have an example. Let's say we want to know which of the following, I showed you the answer, sorry, okay, there you go. We want to know which of the following are discrete random variables. So the first part of the example, the number of tellers in a bank. Now the number of tellers is going to be a count, right? Could be 0 if there are no tellers, 1 or 2, 3, depending on how many tellers there are in a given bank. So because that is simply a count, so it qualifies as a discrete random variable. The middle part, how fast a person drives on the freeway. Remember, measured quantities are continuous. Now, how fast a person drives, the speed of that automobile, or how fast a person drives could vary. It could be any real number between, let's say, 40 to 100 miles, 120 miles, whatever that upper limit might be. But the point is that in that interval, the speed can assume any real number. It doesn't have to be finite or countable. Okay, so how fast a person drives is not a discrete random variable. And finally, the stated minimum wage in a particular state. Notice I said stated. So for example, in California for now, let's say it's $11.50 an hour, $11.75 an hour, $12 an hour. In another state, it could be $10 an hour, $8 an hour. These are countable or finite values. So that variable too would be discrete. Next, we're going to talk about a probability distribution. So what the probability distribution again is if what it does for us is really it does just that. It shows how the outcomes or the values of the random variable are distributed. Okay, so we usually like to get a visual of the probability distribution. With discrete probability distribution, the way this distribution is going to look is that it's going to be a table. It's going to be a table for us, and it's going to have two entries in it. The table will have a listing of the outcomes of a random variable and then the corresponding probabilities. Now, the random variable, by the way, we're going to use letter X for it. That's just the generic X. We use X in everything in mathematics as X, the variable. But it could be a descriptive letter too. So if I'm talking about weights, I can call the random variable to be W. If I'm talking about speeds, it could be S. If I'm talking about wages, it could be W, and so on. So here I have an example that this is the probability distribution for the number of accidents fatalities on a 4th of July. Okay, so let's say I went back to about 30 years worth of data, and this is just on 4th of July. Okay, and now this is in a selected city in the US. So let's say this is in San Diego, this could be in Los Angeles, New York, Houston. It's just one city. It's not statewide and it's not nationwide figure. So X is the number of accident fatalities. So the number ranges anywhere from 0 to 1 to 2 and 3. Okay, so 0 means no fatalities. 1 means just that, exactly 1. 2 means 2, 3 means 3. They're literally what they are. Now notice that's the listing, that's the outcomes of the random variable I was talking about. So the outcomes are again listed 0, 1, 2, 3. Now the probabilities of these outcomes, probability of no accident here is going to be 55%. Probability that there will be one accident, again, this is based on historical data, so we're going to take this to be like a theoretical distribution going forward. And probability 3 accidents would be 5%. Okay, now something I made sure is that these probabilities add up to 1, so I got 55, 80, 90, 100%. Looks good. And we'll look at that in a minute, what makes a probability distribution a valid probability distribution. Okay. Now, as far as the letter goes, we use capital letters to indicate the name of the random variables, and we use lowercase letters that go with that capital letter. So if it's R, capital R for rent, little r would be a specific value for rent, $1,500, $1,800 per month, and whatever. So capital P means probability, and I have probability of CapEx equals little x, means probability the random variable x will take on a numerical value, little x. And I have an example for you. Let's say capital X is going to be the price of a used automobile. Of course, depends on the automobile, right? Let's say this is a Toyota or a Hyundai or something. $5,000 is probably about 10 years old. Then if you say capital X is $5,000, that means that defines an event. Notice there's no probability next to that. That's just the event that the price of a used automobile will be $5,000. Once we put parentheses outside of that, then this becomes probability statement, and it means we want probability of that event. Okay. Now let's take a look at the two attributes of any probability distribution. The two attributes are, first, for any particular outcome, the probability of the outcome must be between 0 and 1. So if you look at this example I have, all of these numbers, the probabilities lie between 0 and 1. So that's good. And the other thing I had to make sure is that these add up to 1. If they don't add up to 1, they add up to, let's say, 85%, that means there's a 15% at large that's not listed. So that invalidates the probability distribution. If they do not total, the probabilities do not total to 1, then the distribution is not a valid distribution. Okay, so here I have the rules for valid probability distribution. 1, individual probabilities for a given outcome must be between 0 and 1, and here I have outcomes 1, 2, 3, blah blah blah, all the way up to the nth outcome, whatever that might be. Okay, and then some of the probabilities must be 1. Okay, and we got to make sure that they add up to 1. Okay, and then let's see. So here I have these examples. I think I have, there you go. I won't show you the answers yet. Okay, so I made up 3 examples, and let's see which of these are valid and which ones are invalid. Now, if you look at the first one that reads probabilities here, Now remember, the outcomes could be negative. The outcomes happen to be 0, 1, 2, 3. If it's warranted for a negative outcome, if we can justify it, then we'll do that. But usually, because these outcomes are counts, they're not negative. But they could be negative, again, because like a negative 1.5, negative 2, negative 1, those are finite values, not countable in the sense that they're positive numbers, natural numbers, but they're finite numbers. So the outcomes do qualify as discrete. In our work, we're not going to see negative outcomes. So, but that's not the key here. The focus is on the probability statements. So if I add up all of the probabilities in part A, so I get 15 and 25, that's 40, and 45, that's 95 and 20. See, that exceeds 100%. Individually, they're fine. They're between 0 and 1. So the first presumption, the first rule is met, but the second one is not. So A is not a valid probability distribution. Okay, because some of the probabilities surpass 1. In part B, let's go through the same analysis. For part B, we have 55, 30, 25, negative 10. Now there you go. The problem is right in here. Negative 10. Probabilities must be between 0 and 1. So we cannot make them add up to 1 by creating negative probabilities. Now in this one, actually, if you notice, the probabilities do add up to 1. It's just an invalid way of adding them to 1. That negative 10%, impossible. So that makes B an invalid probability distribution. In part C, now part C, if you look at that one, we got 55, 25, 15, 05. And this one looks fine, doesn't it? Because they add up to 1. And individually, the probabilities are between 0 and 1. Now, for this one, the way I made this one up, by the way, if you note, the outcomes are negative. That's not a problem. That's not an issue. The focus is on the probabilities. Okay, so C is a valid probability distribution. Okay, so hopefully I was able to get that point across to you. Now, these probability distribution, by the way, I have it, they resemble frequency distributions. And in fact, when we talked about frequency tables way in the beginning of the semester, when we had just simple examples, and we created frequency and relative frequency distributions, I did mention we like to look at relative frequency distributions because they will tie in with probabilities later on, and this is precisely where they tie in together. So now, what is a probability distribution good for? What can we use it on? Well, once we have the probability distribution, then what we can do is we can define events related to the outcomes, and we can assess or establish the probabilities of those events. Okay, so that's at least that's what it's good for. And it has its other usages also, but for now, that's what we would like to do in this section anyway. We just want to take on that idea. So we're going to define events, and we would like to be able to define probability of events. Now, when it comes to probability statements that we make, semantics play a key role in writing and finding these probabilities correctly. So we're talking about the semantics of at least, at most, no more than. Whether some event defines outcomes, where the outcomes are included or excluded from the event. So are these outcomes inclusive or exclusive? So all of these semantics, again, play a key role. When we say and, when we say or, so these are, again, all important. Let me just add those on there. When we say and when we say or. So these are all important notions for us. So let's take a look at this example that I had earlier. And we want to define these events. Okay. So in this example, again, we saw this earlier. This is the number of fatalities in an auto accident on a given 4th of July in a particular city. So I've defined 5 events. Notice we define the events, right, in context of the experiment. So here event A is that there are no fatalities. Event B, there is at least 2 fatalities, and so on. And we want to establish the probabilities of these events. So let's see, in part A, probability that there are no fatalities. Well, no fatalities means the outcome is 0, and probability of that we can see is 55%, right? 0.55 right here. That's 55%. So probability x0, actually I left the probability out in this one, so let me insert that outside parentheses. Without it, it's just an event, so now that's a probability. Okay, so that probability is going to be 55%. Okay, in part B, probability that there is at least 2 fatalities. Now think about at least 2. When we say at least 2 means 2 or more, right? So in this example, it would be 2 or 3, because we don't have 4, 5, 6, and so on, so we stop with 2 and 3. So probability of at least 2, then that means probability of x equal 2 or 3. Now remember when we talked about the addition rule of probability, event x equal 2 and event x equal 3 are disjoint. They cannot happen together. If you have 2 fatalities, you cannot have 2 fatalities and 3 fatalities at the same time. It's one or the other. You either have 2 or 3. You can't say, well, I have both. We don't count them that way. So probability of x2 or 3, therefore by addition rule for mutually exclusive or disjoint events, is going to be probability of 2 plus probability of 3. And notice we get these numbers directly from the table. Probability between 1 and 3 fatalities inclusive. Inclusive means you actually include 1 and 3. So there you go. This is how we write it. And probability is going to be 1 or 2 or 3. You add up those individual probabilities again, because those are disjoint events. And the total probability is going to be 45% in part C. Part D, same kind of probability statement. I just changed the keyword inclusive to exclusive. Now exclusive excludes the value, so the endpoints are now excluded. So probability between 1 and 3, well, if I'm not supposed to count 1 and 3, that just leaves me with 2, doesn't it? So this becomes the same as probability of exactly 2 accidents, and that's 15%. And we go to part E, probability fewer than 2. Now again, fewer than 2 means 1 or 0. And that's directly from the table. We obtain that to be 80%. Now, let me continue on. So, based on what we just observed, look at parts D and C. C and D here. Both of them have between 1 and 3. One includes, the other one excludes. And note, the probabilities are way different, right? We have 45% probability versus 80%. So whether we include the endpoints makes a big difference in the case of a discrete probability distribution. So for a discrete probability distribution, I have it, whether you include or exclude an outcome, it will affect the probability. Okay. Now here I have, it's like, well, where do the probabilities come from in a probability distribution table? Well, one is you can look at historical data. So for the one I have for fatalities on 4th of July, well, you can look at the number of fatalities over past 5 to 20, 50 years. Those have to be on 4th of July. We're not talking about any other event. So that's our special focus, is on that given day. So that's how we can get them. We can tally those and create a table and see in the last, let's say, 20, 50 years, how many of those there were no accidents, how many had 1, 2, and what was the maximum? The maximum was 3 in that city. We're talking about a particular locale. So in that city, it was 3. So that's how it can come up. Another way these probability distributions can come up is we can actually have a theoretical model, a function, if you will, a probability function, that is, which generates these probabilities for us. Okay, and we will look at some of these. There are quite a few well-known probability distributions, and we'll look at a couple of those later on. Okay. And what else can we do with them? Well, here I have a list of some of the things you can do with them. There is more, but I just listed something that we are familiar with already. So we can do a histogram. We can find the mean. We can do the median. We can find percentiles. We can do deviations. Anything we've done so far, we can do with probability distributions as far as summary statistics are concerned. Okay. And let's take a look at the probability histogram here. Now, the probability histogram of a discrete random variable looks slightly different than a histogram of a continuous variable. Now, let me also mention that in some textbooks, including the book we're using in this course, in some textbooks, the book actually uses a continuous bar. That means the spikes that you're looking at are actually closed. They have closed just like a regular ordinary histogram is. Now I chose to use the spikes because these are probabilities at a specific point. So I don't like to use a continuous bar that shows continuity. And I can see the authors who use that, what they want to do is, one, because the students are familiar with histograms, so they want to maintain continuity of how they've seen it, they're used to seeing it that way, and that's fine. And the other reason they do that, for those authors, those textbooks that use a continuous bars that are attached, they want you to kind of see the flow of the distribution, how it flows, which aids in recognizing the shape of the distribution. So again, I recognize and I appreciate that, but this is how I'm going to show my probability distributions. So in this particular distribution, if you look at this distribution, the distribution is skewed to the right, and there you go. This is the kind of distribution that is skewed to the right. And again, if you want, you can give this an impression of continuity. The other textbooks, they kind of do this. They connect these bars together. And sorry, it's sloppy, I know. But I just want to show you because I'm going to erase these. And this is how they represent the distribution using these continuous bars, just like you have seen them before. And there you go. So if I do the notation or this, the way the books use continuous bars and histograms, this is what this distribution is gonna look like. There, you see that? That's like a histogram. But again, I'm just gonna stay with the spikes. And I actually used StatCrunch to do this. So the software I used was a StatCrunch, and I'll show you how to do this in an example. StatCrunch is capable of giving us the distribution's shape, which is the histogram, and it does more than that. It can actually also find probability statements for us. So now let's take a look at an example, and I have a note here that some textbooks, especially science textbooks, call these masses. These probabilities are called weights or masses acting on a point. Especially in physical sciences, they call these masses. Very common, we call these weights. So probabilities are masses, they're weights acting at a specific point, discrete point that is. And in fact, I think StatCrunch, will go see it, StatCrunch calls them weights also. So don't be surprised if that's what's called. So we're going to do this exercise, and we're going to do this, we're going to answer it, of course, ourselves, but we're going to do this in StatCrunch. So I'm going to actually rely on StatCrunch in getting the answer to the probability questions. Okay? So in this exercise, what we have is the following. It reads, from the document American Housing Survey for the United States, published by U.S. Census Bureau, we obtain the following frequency distribution for the number of persons per occupied housing unit, where we have used 7 in place of 7 or more. Okay? And the frequencies are in millions of housing units. So notice this is actual data. Now, because this is for the population, assuming census information is for the population, and assuming you're counting every member of the population, which isn't true, but we're going to make that assumption anyhow, then these become population figures, right? And we can treat this as a probability distribution for number of people per housing unit. This is what we're going to assume the theoretical distribution is, and it is at least for the year the census was conducted in. Okay? Now notice we have frequencies here, right? We don't have probabilities, but we can turn these frequencies into relative frequencies, and then those relative frequencies become probabilities, masses, or weights that we need in order to answer the questions. So let's do parts of this exercise now. Okay, in part A, identify the possible values of the random variable y. Okay, notice the book is calling this y instead of x, but that's fine. Usually we use x, y, z's, the latter part of English alphabets. But you could have picked p also for persons here. Okay, so identify possible values of y. All the possible values are 1 person, 2 persons, 3, 4, 5, 6, and then because it's 7, remember 7 represents 7 or more. But those are possible values of random variable y. In part B, use random variable notation to represent an event. See, we can represent an event, not the probability of an event, just the event itself. An event, the housing unit has exactly 3 persons living in it. So that's going to be y. Remember the name of the random variable, capital letter, is y. So this would be up here in the table. I have capital letter y. And these are individual values, little y, so that's what those are. Okay, so using random variable notation, that event is y equals 3. Don't put a probability in front of it. He just defined an event. Okay, and in part C, determine probability of y equals 3. See, now he defined an event, now we want to find the probability of that event. So probability of y equals 3, interpret in terms of percentages. Okay, so we're going to look at, remember the classical definition, possible over total, possible outcomes. There's 17 million people that qualify. Now the total of these, I've calculated the total of these. And if I did it correctly, here the total number of households that's in that census information was 105.3 million status. That's a little over 105 million, 105,300,000 households. Okay, that's what it is in the census. So that's how many households there are in the U.S. Again, as of that census, that's not accurate because houses are being built all the time, and by the time they publish this information, many more households were established and made. So this is more of a snapshot of at that time. So if I go 105.3 in the denominator, and you do 17 divided by that, that's going to give us the answer. 17 divided by 105.3 gives me 0.1614. Now the question mentioned interpret in terms of percentages, so that's equivalent to 16.14%. So we can say that 16.14% of households in the US have exactly 3 people in it. Okay, and in part D it reads determine the probability distribution of Y. I'll do this in StatCrunch just so it looks nice, and construct a probability histogram. So first we want probability distribution. Remember, that means we want X and probability of X, right? We have 1, 2, all the way to 7. See, right now he has frequencies. He doesn't have probabilities. So we need to create probabilities. Now these probabilities equal relative frequencies. Keep that in mind when we have the data. So it's just I need to determine these numbers, and we do these in StatCrunch, and I just copy and paste them onto this. So let me go to StatCrunch and actually complete this exercise. Okay, so I am in StatCrunch now, and if you can see, I have persons 1, 2, 3, 4, 5, 6, 7. I actually have to input these manually because unfortunately he doesn't have these. I would have put them in chapter 5 because otherwise you have to type them in yourself. But see, they're not available to my left here. There's not a clickable link that I can click and bring up the data. But beginning in chapter 6, see, you can import the data in. But for now, we just have to type them in. So I typed persons, that's my variable, and then I have frequencies. I actually type those in. Now, let's create the probability distribution here. So to do that, I'm going to actually type here. Okay, I'm going to type this is probability capital X equals we're using Y, sorry. In the book, remember, he used Y. There. Now, we actually want StatCrunch to fill in the relative frequencies for us, right? So here's how you do this. We're going to go to Stat, and let me see. Let's go to, actually here, let's go to Data. I have Data, and we're going to go Compute and Expression. That's what we want to do. Okay, so Data, Compute, and Expression. You can do this on a calculator and type it in yourself because the table isn't long, but it's just good to know how to do this in StatCrunch. And I want to build this expression. Click on Build. Now, in this build expression, how am I going to do this? I would like to divide. Remember, relative frequencies are when you divide individual frequencies by the total. So I'm going to use variable frequency, double click on that, and then / means we want to divide it. We're going to divide it by the total, right? That's the sum. So I'm just going to type the keyword here is sum, and then open parentheses, double click on frequencies, close parentheses. See what I'm doing? So I'm dividing an individual frequency. In the case of first observation, we're dividing 27.9 divided by sum of the frequencies, which I mentioned is 105.3, but I don't need to type 105.3. Using this built-in sum function, StatCrunch will do this. And then come here, down here, and hit OK. And compute. Notice it's inside the expression here. Hit compute, and right in here, actually the values are brought into their new column, frequency added to data table. Okay, and let me go options, edit, column label. Okay, sorry about that. I could have done that. Instead of calling it what it called, I can call it, that's the relative frequency column, probability Y equal Y, little y. Okay, and compute. And because I renamed it, it created this additional column. So let me X this out Now, notice these two columns are redundant, right? These two columns are redundant. First of all, I'm going to delete the column I created here. There, I don't need it. Notice how these are identical columns. I don't like the verbiage, how this one is labeled. I'm going to delete this one. And now I have the column that I wanted. So this is now what the answer to the exercise is. Okay, so I'm just going to copy these columns, these two columns, and bring them over to my notebook. Okay, and there they are. So this would be the answer to part D of the exercise, determine the probability distribution. Notice how the probabilities are relative frequencies that we obtained from the data. Now in part E, construct a probability histogram of Y. Now to do part E again, I'm going to go back to StatCrunch and actually show you how to get a probability histogram from StatCrunch. So let me get this prepared and let's go to StatCrunch again. Now I'm back in the StatCrunch again here. Let's take a look at how we're going to get a histogram of this probability distribution. So we're going to go to Stat, then we go to Calculators, and in here we're going to go all the way down to Custom, because this is the one that's custom based on census data. So notice there's a whole host of well-known distributions here. Okay, so we're just going to look at this custom distribution. Click on custom, left click once. And now the values in. So where are the values in? Well, the values are persons, right? Those are the values. And notice how StatCrunch calls probabilities weights. Weights in means where are the probabilities? Well, the probabilities are in this column, right, that we created, the relative frequency column. And hit compute. And there you have it. So this is going to be the probability histogram for this data. Now, I'm going to copy paste just this top portion. The below portion, the bottom portions, we'll look at these later. But notice in here, by the way, you can actually answer probability questions about this exercise, and we'll do that in a few minutes. So if you click here, the direction for probability, if you click on the what we call inequality, you're going to see some options here. Let me click on it, and there you go. You can find probability of exactly 2. Exactly 2 is 32, 66, 85, 66. And also the bar, notice the bar at 2 is now painted in red. So it actually shows you the event, probability of event. So it tells you what the outcome is that goes with the event. If I want probability of less than or equal to 3, you just type that in. And now the bars 1, 2, 3 are highlighted. Not highlighted, but they're now in red. But I want to know what is probability of more than 5. More than 5 per housing unit. That's going to be 6 or 7. Those two add up to 0.35. And so there you go, so on and so forth. If you want to know probability of less than or equal to 5, that's 96, better than 96%. So you see how you can answer all the probability questions right in here about this exercise. So let me again bring this to my note. I'm going to save this because we're going to use it in a few minutes to answer probability questions. And I'm going to just copy paste it in my note. And here it is, this histogram for exercise number 8, done in StatCrunch. Again, don't worry about the colors of the bars being red and so on. Now, we mentioned one thing we are interested is in distribution of the random variable. So it looks like the distribution of number of people, persons per housing unit follows a rather skewed distribution like that. So that's the general impression we get from this. We can make it a little more accurate and make it like this. And there we have this one. Okay, so that's what that is. And with that we are done with this exercise. And let me see if this exercise continues on with some probability questions about it. Well, it doesn't look like it does, but again, we can make our own probability statements and answer those probability questions. So for example, let's say I want to know, these are just extra problems I'm making up. What is probability a random household will have two people living in it, exactly two people? Well, probability of two people is 3267. See how simple it is? Once we have the table, we just directly find these probabilities. What is probability that there is no more than 3 people? Less than or equal to 3. Now I have to add these 3 numbers, right? That's going to be, I'm just rounding these, 0.2649. Actually, let me go 0.265. I'm going to go to the nearest thousand. Plus probability, that was probability of 1. Probability of 2 people in it is 0.327 plus 0.161. Okay, so that's going to be the answer to the probability. And if I add these up, 0.265 plus 0.327 plus 0.161, I get 0.753. Again, about 75% of households in the US have no more than 3 people living in it. What if I want to know what is the probability that a randomly selected household will have between 3 and 5 people in it, inclusive. So between 3 and 5, I just add these numbers, right? That's going to be 16.161 plus 0.147 and plus 0.065, but 6.5% that last number is. Now if I add up these numbers together, 0.065 plus the other 2, I should get 0.373, almost, let's call it 40%. And that was inclusive. Now if I said between 3 and 5 exclusive, let me just write it. Between 3 and 5 exclusive, then that means just, well, if I can't have 3, I can't have 5, and then I have to have only 4. That's 0.147. Again, a notable difference in probability. It's by a tune of about 23% less. So there you go. So with that, we are done with this section. We're going to continue on with this exercise in our next section. But for this section, we are done with section 5.1.